Hello everyone. I realize that there are lots of confusion about conversion factors. And as you saw, I gave really easy questions in your exam, including conversion factors, but we are going to use them a lot. That's why I gave you more challenging questions in these homework assignments. And to help you learn, I also solving them. But I just changed the numbers or like materials that I gave you in the homework problems so you actually learn the problems, not simply copying and pasting from this video. So let's solve the problems. And I already wrote the question, so this video would be shorter. So I make sure that you watch it. And I simply ask you to watch it. Okay. The first question that I gave you in your homework assignment number 6 is a specific heat capacity and converting different units. It says the specific heat capacity of ethanol is 2.42 joules per gram per degree Celsius. Write this number in calorie per pounds per Kelvin, knowing the following. 1 calorie, and remember, this is like this small letter, C. So calorie and calorie are different. And you can use your book to see how you can convert them to one another, but I'll give you in the exam if I ask you to convert them, like here, that I ask you to convert calorie to joules, I give you the conversion factor, so don't worry about it. So, and then I gave you 1 pound equals 453.59 grams. Again, anything that you want to find, you write question mark. Specific heat capacity of ethanol is this much. Write this number in calorie per pounds Kelvin. So this is what you want. Question mark, calorie divided by pound multiplied by Kelvin equals what you are given. You are given this number. Although you have this information, but these are your conversion factors. This is the thing that you want to find. 2.42 joules per gram degree Celsius. Okay, so here what that you want to find, this is what you are given. Multiply by, you have like 3 different units that you want to convert. So you should write 3 conversion factors. So first, whichever you want to convert first. I just started joules. Again, you want to get rid of joule, right? So you write joules here in denominator so it cancels with numerator. And we want to convert that to calorie. So I write calorie, and remember this is a small letter, calorie in numerator. 1 calorie equals 4.184 joules. Okay? So I took care of, energy so far. I changed the color here to this blue, dark blue. And gram. I want to convert grams to pounds. So here I write gram in numerator so it cancels with denominator. And I'm given, like here, pounds. 1 pound equals 453.59. These two quantities are equal. That's why this conversion factor is 1. Mathematically, that's why we can multiply it by a number. If I have like number 20 and I multiply it by 1, it's still, 20. That's the whole rationale of using conversion factors. 1 calorie equals 4.184 joules. This would be 1. So I can multiply ones by the number that I'm given without changing anything. I hope that makes sense. Okay. Now, here is kind of like the part that can be tricky to some of you or anyone that doesn't know this. So, degrees Celsius, we have, remember, in the heat equation, MC delta T, we have difference in temperature, okay? And if I have a number in Kelvin, and I want to convert it to Celsius, remember what was it? Kelvin equals degrees Celsius plus 273.15. right? So you see that if I have like two temperatures in Kelvin, so if I have like, again, remember here, we want temperature difference. So it's like T at like 2 minus T1. So, or you can say T at final state minus T of the initial, right? Meaning that you report temperature difference. When in the problem so far, I gave you temperature difference. I said the temperature difference is like 20 centigrade degree. But I can also give you that my initial temperature is like 10 degrees Celsius. My final temperature is like 20 degrees Celsius. And then you should calculate temperature difference. But, pay attention that if I have like, T1 and T2 and I report them in Kelvin. So I say K2 minus K1 to emphasize that these are like in Kelvin. And I want to calculate the equivalent in Celsius. I write, okay, Celsius plus 273.15, right? Minus degrees Celsius in the initial or like the state 1 plus 273.15, right? So I say K2 minus K1 equals degrees Celsius at state 2 plus 273 minus 15 minus degrees Celsius 1 minus 273.15. And these two numbers cancel out. So you see temperature difference in Kelvin would be the same as Celsius. And I guess the better way of writing this is that you write T2 in Kelvin minus T2 in minus T1 in Kelvin equals degrees Celsius plus 273.15, or like you can say temperature in secondary state, or like, T2 in degrees Celsius minus T1 in degrees Celsius, plus 273.15. Or I can, minimize this. So I can write it here. Equals T2 in degrees Celsius plus 273.15 minus T1 in degrees Celsius minus 273.15. So you see these two cancel out. Equals to T2 in degrees Celsius minus T1 in degrees Celsius. Meaning that delta T in Kelvin equals delta T in degrees Celsius. Meaning that here you don't have to do any conversion factor, because degrees Celsius, 1 degree Celsius, because it's temperature difference, in degrees Celsius equals 1 Kelvin. Does that make sense? If this is kind of like hard for you to, comprehend just based on the formula, just give yourself an example. So imagine you have like, you have your initial temperature like 10 degrees Celsius, and then your final temperature 20 degrees Celsius. And you say, okay, delta T equals T2 minus T1 equals 20 minus 10. And these are like just examples, It's not part of your problems. I'm just trying to demonstrate a point. Would be 10 degrees Celsius. Now you want to convert these 10 degrees Celsius, to Kelvin. Or rather, let me do this. If you convert each of these temperatures to Kelvin, would be like 10 plus 273.15 would be 283.15 Kelvin, right? And your T2 would be 20 plus 273.15. It would be like 293.15 Kelvin. Now let's calculate temperature differences Kelvin. T2 minus T1, 293.15 minus 283.15 equals 10 Kelvin. You see, in both cases you have the same number. That's why temperature difference in degrees Celsius equals temperature difference in Kelvin. So here now that we know that, we just substitute the numbers. 2.42 multiplied by 1 multiplied by 453.59 divided by 4.184 and write the units as well. Everything canceled out. We have only calorie divided by pound multiplied by Kelvin, right? And I just put this number in my calculator, so I have the final answer for you guys as well. Divided by 84. Make sure to put the number in calculator correctly. 262.35 calorie, and this is lowercase calorie. Don't mind my handwriting. Calorie. Okay. So this is how we solve this question, and feel free to email me if you have any questions. The second question. A chemist needs an 8.72 pound sample of ethanol. What volume in gallon of ethanol should they use, knowing the density of ethanol is this much, how to convert pounds to gram, how to convert liter to cubic centimeter, how to convert gram per liter. Again, anything that you want to find, write question mark that then. What do you want to find? Volume in gallon. So you say how many gallons, or I write gallon as itself, or you can say GAL, equals 8.72 pound. Remember, pounds. Remember, anything that you want to find, rewrite question mark that thing, equals to the thing that are given here in your question statement, because here these guys are your conversion factors, remember. So multiply. How can I convert pounds to gallon? So I want to relate mass to volume. Remember, we do that with density, but here in density I have a gram per cubic centimeter, so I have grams, so I should convert pounds here to grams. Is that clear? So to convert grams to pounds, I should refer here. I'm writing conversion factors. Remember, 1 pound equals 453.59 grams. Okay? So these cancel out, pounds. Multiply by. Now I have grams here in density. I can convert that to cubic centimeter, and I write gram in denominator, so it cancels out with my numerator. And this number means that when I say the density is like 0.789 gram per cubic centimeter, it means that 1 cubic centimeter of ethanol, for 1 cubic centimeter ethanol has the mass of 0.789 grams. Okay. And now I should convert cubic centimeter to what? I want to convert that to gallon, but I don't have a direct conversion factor here. So I need to first convert cubic centimeter to liter, and then convert, these two cancel, liter to gallon, right? So 1 liter is like 1,000 cubic centimeter, and then 1 gallon is 3.785 liter. These two cancel out, you see? So my final answer would be 8.72 multiplied by 453.59 divided by 0.789 multiplied by 1,000 multiplied by 3.785, and you see that would be this much gallon. And I just put the number in calculator so I can write the final answer for this question as well. Multiply by 453.59 divided by 0.789 multiplied by 1000 multiplied by 3.785. 1.32 gallons. Okay, let's go to the next question. Convert 300 Kelvin to degree Fahrenheit. And I just realized this is exactly the same number that I gave you in your homework, so I'm going to change this to 1000 Kelvin to degree Fahrenheit. Remember the formulas. I asked you to remember this. So degree, basically not degree. We don't use degree for Kelvin. Kelvin equals degree Celsius plus 273.15, and degree Fahrenheit equals 1.8 degrees Celsius plus 32. So here I gave you 1000 Kelvin, right, equals degree Celsius plus 273.15. So from this I can find that, degree Celsius is 1000 minus 273.15. So 1000 minus 273.15 equals 726.85 degrees Celsius. And I substitute this number here. So degree Fahrenheit equals 1.8 multiplied by 726.85 plus 32. And remember, first you multiply and then add. If you get confused, just put a parenthesis to be safe. 1.8 multiplied by 726.85 plus 32 would be 1340.33 degree Fahrenheit. So this is how you solve this question. Okay, let's go to the next question. This can be tricky, so pay attention. A 20 grams silver block is warm, or a silver block that has a mass of 20 grams is warmed to 60 degrees Celsius and is plunged into an insulated beaker containing 20 grams of water, initially at 25 degrees Celsius. The silver and water are allowed to come to thermal equilibrium. Assuming that no heat is lost, what is the final temperature of water and silver, knowing their specific heats? Basically, you have like a silver block, okay, and you warm that to this temperature, right? And then you have like a beaker that has this much of water, okay, and you put that basically plunge that in that silver block to the body of water. So imagine, and then that is insulated, meaning that you only consider the water and the beaker that has the water and also your silver block. So this is a good example that if you consider the concept of system, it can help you to solve this problem. So imagine if this is my beaker and it has like water in it, right? And then I have like a silver block and it has like, a certain temperature, initial temperature. So T initial of this silver block is like 60, right? And I put that in the water and in the beaker that has like certain amount of water, and I let them to reach equilibrium. Basically, I wait enough for them. When I put this silver to the water, I wait for them to reach to the same temperature, basically to reach equilibrium, so that they don't transfer heat anymore. But first, at first this temperature of water is, let me have another color here, it's And maybe it's like, visually more appealing if I have like the lower temperature with blue, hotter temperature with red. So imagine I have like my water, and the beaker, right? That has, let's see, I have my water initially, degree of 25 degrees Celsius, okay? So T initial of water is 25 degrees Celsius. And I have like this block of silver, right? Write it like this. That T initial of silver is 60 degrees Celsius. So, it's good that you, try to have like a sense of the problem that you're solving. This is like much hotter compared to my body of water, okay? And what I do is that I put this in my system. If I consider like this, my beaker, or like your body of water, but I kind of like, mark beaker as my system because this is like insulated, meaning that the only thing that is happening in this system is that this silver, transfers heat to the body of water, but this, body of water, this beaker, does not transfer any heat to the surrounding, or it doesn't receive any heat from surrounding, or we don't have anything else happening. The only thing that is happening is that I have like this, silver block that is hotter than the water. So when I put it in my water, it gives thermal energy to my water. So water gains thermal energy and its temperature increases, and this silver block loses thermal energy and its temperature decreases. So I hope you have an understanding of what is happening here. And we say that no heat is lost, it's meaning that, we don't, everything that is happening, we have just like, Q of water, or rather the Q that water, the thermal energy that water gains, and also thermal energy that the silver block loses. So we have like, we can write, remember the equation for Q, heat, equals mc delta T. We can write this equation for water, and we can write this equation for, silver. If I write that for water, so first I start with water and I write that here, so I have like more space. If I write Q equals mc delta T for water, what should I write? I don't know the Q, do I? No. I write M. I have like M of water, right? We, problem statement said that I have like 20 grams of water, right? Multiply by, and always write the units. Specific heat capacity of water, 4.184 joules per gram degree Celsius. Multiply by delta T. T final I want to find, right? I want to see what would be the final temperature of water because we put something hot in it, so temperature of water increases. But I have the initial temperature, which is like 25 degrees Celsius, right? So this is the first part. And I can write the same thing for the silver block, right? So if I write that again, Q equals mc delta T, Q, I don't know what Q is yet, right? And what is the grams of silver? I gave you the same number, apparently. 20 grams of silver multiplied by a specific heat capacity of silver, which is 0.235 joules per gram degree Celsius. Multiplied by T final, I don't know what it is, minus T initial that I know it is 60 degrees Celsius. So here's the tricky part. So here I write Q of water, here I write Q of silver. If I consider my system here, the beaker, right, and I put something hot, silver block in water, and I write water with blue. The heat that silver block gives to the system goes to the water, right? I say that again. So thermal energy, of silver goes to body of water because this is the only system that we're considering and the system is insulated. So this Q, that silver gives to water equals the Q of water. So basically some thermal energy is being transferred from silver to water. And the heat that is being released from silver goes to water. So Q of water numerically equals Q of silver, but they have opposite sign. Because if you consider your block of silver, I write that with red, Q goes out of it, so it's positive, right? If you consider this as your system. If you consider the body of water, and I write the body of water like this. If you consider this as your system, so sorry, this one, the beaker gives, releases heat. It goes out of it. It goes out of the system. But when you consider body of water, Q comes into it. So it receives this amount of energy. Does that make sense? So these two numbers are, if I write Q of silver, basically one of them, Q of water equals minus Q of silver. Because, silver, if you consider that as the system, the energy goes out of it. Remember, kind of like it's the same concept as like endothermic, exothermic reactions, except here, no reaction is occurring. It's just like heat transfer. So silver, releases energy, it goes out of it, and then water receives this heat. So heat, goes out of like silver and goes to water. I hope that you understand why this is the thing that is happening. So these two numbers, like Q of water and Q of silver, numerically equal. But if I have, for instance, 20 joules heat released from silver, because it has highest temperature, water receives 20 joules. Does that make sense? Kind of. And again, please, before doing your homework assignment, if you have question about this, just email me and I explain this further to you. But this is, I guess, the best that I can explain it through the video. That the amount of heat water receives is the amount of heat that silver releases. Okay, now let's solve the equation. So you have 20 multiplied by 4.184 multiplied by T final minus 25 equals 20 multiplied by 0.23235 multiplied by T final minus 60. And remember, one of these, so here when I substitute, I should also put negative here. Remember, one of them should be negative. And you can also, so I wrote here, any of these, you just should remember these two numbers are equal in number, in magnitude, but one of them is negative because the heat that goes out of silver block that it releases would be gained by water. Okay, so if I multiply these guys, and remember, we don't round intermediate results. 20 multiplied by 4.184 would be 83.68 multiplied by T final minus 25 equals minus 20 multiplied by, and I didn't even have to multiply 20, I could just like cross them out, but oh well, I just did that. So I'm just gonna continue writing what I wrote. T final minus 60. So I can write T final minus 25, dividing both sides by like, T final minus 60, right? Equals minus 4.7 divided by 83.68. So that number would be 4.8 divided by 83.68, 0.056. You can just like do that in your calculator so you don't have to write the whole thing. T final minus 25 equals minus this number, T final plus this multiplied by this, right? And I already multiplied this number by, so minus 0.056, this number multiplied by minus 60 would be 3.3699808795. Okay. So, you have like a sense, you have like 60 multiplied by 0.05. So if 5 multiplied by 100 divided by 100 multiplied by 60, it would be like almost 3, right? So just like check your answer. And T final plus 0.056. And again, these things I'm just writing here to demonstrate. You can just put the numbers in calculator. Equals 3.36998 with the rest of the number, write the whole thing, plus 25. I have it here on my computer, so I just add 25 to that. And remember, the number should be roughly 28, right? So if you get something else, you did something wrong. Equals 28.36998, and 1 plus this, remember you factor T final, would be 1 plus 0.056, right? So I have this number here, plus 1, right? So T final would be 28.36998 divided by 1.05616634799. When you do that, the final answer would be 26.86. And the number would be degrees Celsius. Okay, let's go to the last question. Okay, I talked about gas mileage in the class, and when you want to buy a car, or in general, if you look at your car, it has a gas mileage, which is like miles per gallon, meaning that if you have like for 1 gallon of fuel that it burns, how much a car can go. So when a car has like higher gas mileage, economically it's more feasible. So when you want to compare, which one of these two cars, for instance, has a better gas mileage, is the one that is higher, because for 1 gallon it goes further. So you want to, this is one factor that you can consider when you buy a car. So here in this question, I gave you some gas mileages, and I asked you to convert them to kilometer per cubic centimeter. And I also, in the homework problem that I gave you the conversion factors. So how much is, how to convert gallons to liters, how to convert like liters to cubic centimeter, and how to convert kilometer to miles. So I'll do one of them as an example, and hopefully you can just do the same for all of them, So here, for instance, if you want to convert, 28 miles per gallon to kilometer per cubic centimeter. Again, what do you want to find is like how many kilometers per cubic centimeter equals, for instance, 28 miles per gallon. You multiply that by a conversion factor, depending on which one you want to take care of sooner. I want to get rid of gallon. How can I convert gallon to cubic centimeter? If you look at the problem statement that I gave you, we cannot convert them immediately. First, I should convert gallon to liter, get rid of gallon, and then convert liter to cubic centimeter, right? So 1 gallon is like 3.785 liters, and 1 liter is 1,000 cubic centimeter, okay? And now I convert miles to kilometer. And I gave you like 1 kilometer is 0.6214. If this is confusing, I kind of write these guys here, so you know that you are given this information in your homework. Okay? So you just put these numbers in calculator and solve the problem. And remember to write everything, and remember to write neatly so you don't make mistakes. And the number would be kilometer per cubic centimeter. And I put the numbers in calculator. Remember, you should write parentheses for the numerator and denominator. So parentheses open, 28 multiplied by 1 multiplied by 1 multiplied by 1, which would be like 28, divided by 3 parentheses open, 3.785 multiplied by 2 3.785. Sometimes I just read the numbers wrong. You know what I mean, hopefully. Okay, when you put the numbers in calculator, you get like 0.0119 kilometer per cubic centimeter. When you want to round this number, depending on what you are given, so it would be like 0.01 kilometer per cubic centimeter. Or if you want to round it, differently, it would be like more digits. Okay. So this is how you solve the problem, and then for each of these, you just substitute the corresponding number here. The rest of the procedure would be the same. Hopefully this helps.